everyone. Today I am going to read chapter number 13 from Principles of Inorganic Chemistry by Puri Sharma Kalia. Chapter number 24. The elements of the third transition series. The third transition series consists of 9 elements excluding lanthanum, which is discussed as a member of the lanthanide series because of its very close resemblance with the elements of this series. The 9 members of the third transition series are hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury. These elements are much more important than the elements of the second transition series. The general characteristics of these elements have already been discussed in chapter number 21. Some of their physical constants are given in table 1. The present chapter is aimed at describing the chemistry of the individual members of the series in some details. Hafnium. Occurrence. It occurs in zirconium mineral as already stated. In fact, it was first discovered in these minerals by X-ray methods. Most of the zirconium minerals contains this element, ordinarily only up to 0.1% but occasionally up to 7% concentration as well. Extraction. Separation of hafnium from zirconium, however, it is very difficult or on account of their very close resemblance. However, it is now possible to do so by ion exchange chromatography or fractional solvent extraction. The method based on ion exchange chromatography has been discussed in detail in the next chapter. In other method of separation, advantage is taken of the fact that the halides of both the elements, that is HFCl4 and ZrCl4, from stable complexes with phosphoryl chloride POCl3. The two complexes formed are HFCl4 twice, POCl3 twice, and ZrCl4 thrice, POCl3 twice. These two differ in their boiling point by 5 degrees Celsius. This helps in separating the two complexes and subsequently the two elements from each other. There is very close resemblance between hafnium and zirconium as also in their compounds. Tantalum. The chemistry of tantalum has already been discussed along with that of niobium in the last chapter. Tungsten. Occurrence. The minerals containing tungstens are wolframite, which is mixture of iron and manganese tungstenates; scalite, which consists of calcium tungstate; coprochalite, which is copper tungsten. Extraction. The metal is generally extracted from the wolframite ore. The ore is concentrated by electromagnetic process as it contains magnetic impurities. The concentration ore is roasted with sodium carbonate in excess of air when sodium tungstate is produced, while iron and manganese are converted to their respective oxides. The reactions are represented as below. The roasted mass is extracted with hot water to dissolve sodium tungstate. The insoluble ferric oxide and manganese dioxide are removed by filtration. The solution is treated with dilute acid when tungsten trioxide (WO3) is thrown down as a precipitate. This is washed and dried and reduced to the metal by heating with carbon, zinc, or aluminium. WO3 plus 2Al gives to Al2O3 plus W properties. It is hard and has a silvery white luster. It has a very high melting point, which is close to 3410 degrees Celsius. It is higher than that of any other metal. Its specific gravity 19.3 is close to that of gold. Due to its high melting point, it cannot be easily cast into rods or wires. A special technique has been devised for this purpose. The powder is compressed into a rod and heated in an atmosphere of hydrogen, while a strong electric current is passed so as to raise it about 300 degrees Celsius. As a result of this, the powder gas converted into a compact mass, which can then be rolled and hammered at 15 degrees Celsius and driven into wires. Tungsten resists the action of air, oxygen, or chlorine unless heated to bright redness. It is not attacked by acids, however, it dissolves in fused alkalis or fused oxidizing agents like potassium chlorate. Uses. Tungsten wire prepared as above. Because of its extremely high melting point and low volatility, is used largely in making filaments for electric lamps. Another major use of tungsten is in making special steel consisting of 14 to 20% tungsten and 3 to 5% chromium. This steel, due to its extreme hardness even at high temperature, is used in making tools for high-speed lathes. Tungsten also forms useful alloys with chromium and cobalt. Solid tungstate is used as a mordant in dyeing and for fireproofing of certain varieties of fabrics. Compounds of tungsten. Tungsten, like chromium, shows oxidation state of +2, +3, +4, +5 and +6. The compounds in which tungsten is in +6 oxidation states are very important. Oxides, tungsten trioxide, WO3. This is the most important oxide of tungsten. It is obtained from wolframite as described above. It is a yellow powder insoluble in water and has amorphous nature. It dissolves in alkalis forming tungstates when heated mildly. In a current of hydrogen, it changes into tungsten dioxide WO2, which is a brown powder. It is soluble in water. It has a complicated structure containing WW bonds. The oxide WO3, when fused with alkali or alkaline earth oxides, gives mixed oxides whose structures and properties are very similar to those of the corresponding mixed oxides of MO. Tungstic acid and tungstates. The acid H2WO4 is obtained as a precipitate when a solution of any tungstate is treated with hydrochloric acid. If precipitation takes place from a cold solution, alpha tungstic acid H2WO4 H2O is produced, but if the precipitation takes place from a hot solution, beta tungstic acid H2WO4 is produced. The former variety is white in color and is very slightly soluble in water, while the later variety is yellow in color and is insoluble in water as well as in acids except hydrofluoric acid. When dissolved in hydrofluoric acid, it changes into hydrofluorotungstic acid H2WO2F4. When WO3 dissolved in solid hydroxide solution, solid tungstate Na2WO4 is formed, while CrO4 negative is strongly oxidizing. WO4 negative is a mild oxidizing agent. On lowering the pH of tungstate solution, isopolystungstates are formed. These compounds are complicated structures containing the WO6 octahedral units joined in a variety of ways by sharing the coordinates or edges of the octahedral units. When WO4 negative co-condense with the PO4 negatives, SiO4 negative and BO4 negative, heteropolystungstates are formed. Their structures are similar to those of molybdates. A well-known example of a heteropolystungstic acid is phosphotungstic acid H3PO4.12WO3 halides. Tungsten also forms a number of halides which are covalent. The examples are WF6, WCl, 6WCl5, WCl4. Their structures and properties are similar to those of the corresponding halides of molybdenum. Tungsten bronzers. By reducing alkali metal tungsten, example Na2WO4, K2WO4 with tungsten, deeply colored substance are obtained. These substances, called tungsten bronzes, are unreactive towards common acid except HF and alkalis, but are the good conductor of electricity. They have metallic luster and have the general formula MXWO3, where M is equals to Li, Na or K. And the value of X is always smaller than 1. These are evidently non-stoichiometric substances in which M+ ion is always present in industrial sites created by three-dimensional network formed due to corner sharing of WO6 octahedra. Tungsten bronzes can be prepared by number 1. Heating the alkali metal tungstates in a current of hydrogen, reducing the tungstate electrolytically, reducing WO3 with alkali metals in the vapor phase. The colors of tungsten bronzes depend upon the amount of alkali or alkaline earth metal ions. These ions, depending upon their amount, produce varying extents of lattice defects and hence impart different colors to the tungsten bronzes. Thus, the color of NaXWO3 varies from golden yellow to blue violet. The electron produced due to ionization of alkali metal M to M positive ions in these tungsten bronzes are completely delocalized over the whole of the lattice and are therefore free to move throughout the lattice. As a result, the tungsten bronzes become conducting. The tungsten bronzes with X smaller than 0.3 are as good conductors as metals. The conductance of tungsten bronzes decrease with increase in temperature. The tungsten bronzes are largely used as metallic paints. Tungsten blues. Like molybdenum blues, tungsten also forms tungsten blues by similar products. Like molybdenum blues, they have varied composition as WO2.67, OH.33 and WO2.7, OH 0.1. Rhenium. Rhenium was discovered only in 1925. The reason is that for several years before 1925, the element was looked for in manganese ores, but this element actually occurs in molybdenum ores, particularly in the mineral. At some places, the mineral contains up to 20 parts per million of rhenium as the sulfide at ReS. True for the oxide ReO2. Both the sulfide and oxide are readily reduced to yield the metal. Compounds of rhenium. Oxides. Amongst the oxides of rhenium are the dioxide, trioxide, pentaoxide, and heptaoxides. The oxidation state of the metal in these compounds evidently are +4, +5, +6, and +7 respectively. ReO2 is obtained by ReO2 is obtained by heating Re2O7 with the metal at 600 degrees Celsius at higher temperatures. This compound reverts back to Re2O7 and Re. ReO3 is made by heating Re2O7 with rhenium at 300 degrees Celsius. It exists in two forms, red and purple. When heated strongly, it disproportionates as 3ReO3, Re2O7 plus ReO2. Perheniates. Perhenic acid is obtained as colorless solution on dissolving Re2O7 in water. The acid is also obtained by oxidizing the metal on heating in nitric acid or by passing chlorine in suspension of ReO2. It has been possible to isolate anhydrous perhenic acid. The solution when heated gives back Re2O7. Perhenic acid is a strong monobasic acid. It reacts with magnesium, iron and zinc involving hydrogen. It is not a strong oxidizing agent. However, it can oxidize HBr to bromine and Hi to iodine. Alkali metal perheniates are also known. These are colorless and stable compounds. Sodium perhenate and ammonium perhenate are very soluble in water. Potassium perhenate, however, is much less soluble. It appears as a precipitate when KCl and HReO4 solution are mixed. Ammonium perhenate, when heated in nitrogen, gives the nitride Re3 and the metal. Perhenates are comparatively more stable and therefore are not used in as oxidizing agents. Perhenates are reduced by K metal in C2H5OH to give the hydride complex anion. ReH9 2 negative halides and oxyhalides, a number of halides of rhenium in which the element is in +3, +4, +5, +6 and +7 oxidation state are known. A number of oxyhalides are also known. These are given in table 2. Preparation of some of the more important halides in given below. ReBr3 is obtained by direct combination of the elements at 300 degrees Celsius. It is a dark green solid. It has a trimeric structure as shown. The lines between the atoms in this structure do not show the exact bond order. ReCl3 and ReI3 have similar structure. ReBr3 adds up KBr to give KReBr10, K2 ReBr11. ReBr4 and ReI4 are obtained by reducing perhenic acid with HBr and Hi respectively. ReCl5 is prepared by heating the metal in chlorine. When heated in an inert atmosphere, it decomposes into ReCl3 and which is a violet crystalline solid. It reacts with water to give perhenic acid. Unusual oxidation states of rhenium. Re has 0 oxidation state in Re2CO 10 and +1 oxidation state in ReClCO5. The +2 oxidation state is not very common. However, complexes such as ReCl2 are known to be fairly stable. Osmium. Osmium occurs in nature as an alloy of osmium and iridium, usually contaminated with ruthenium. In order to recover osmium, the alloy is fused with alkaline oxidized mixture of potassium hydroxide and potassium nitrate. When ruthenium is converted into the soluble potassium ruthenate K2RuO4. After dissolving and acidifying, the mixture is boiled when osmium distills over as osmium tetroxide OSO4. The latter is reduced to osmium on treatment with hydrogen or any other reducing agent. The potential of the oxidation half cell reaction OS solid plus 4H2O gives to OSO4 plus 8H plus 8 electron is minus 0.85 volt, which means that the potential of the reverse reaction is plus 0.85 volt. This is an appreciable positive value. Hence, osmium tetroxide can be easily reduced in acidic medium. Properties: it is a gray white brittle and fairly hard metal. It is inert in the bulk state. It does not dissolve easily even in aquaresia, although it is not attacked by air. It is attacked by pure oxygen even at 200 degrees Celsius, forming volatile tetroxide OSO4. Due to its hardness and inertness, its alloy with iridium is used in making tips of fountain pens. It reacts with alkaline oxidizing agents to give compounds like Na2OSO4 and K2OSO4. When heated, it reacts with sulfur, giving OSS4, with fluorine, giving OSF6, and with chlorine, giving OSCl4. It shows oxidation states of plus 2, plus 3, plus 4, plus 6, plus 8, and its compounds. The important oxidation states are plus 4 and plus 6. The plus 4 is exhibited in the compounds OSO2 and OSCl4. The plus 6 state is represented by osmate ion OS4 2 negative in sodium or potassium osmate, and also in OSF6, which is obtained by heating osmium with fluorine. The plus 8 state is exhibited in the oxide OSO4. This is the most important compounds of osmium and is also called as osmic acid. Osmium tetroxide OSO4. Osmium tetroxide is a solid melting at 40 degrees Celsius and boiling at 100 degrees Celsius. It is highly volatile and its vapors are corrosive to animal tissue and hence very dangerous, particularly for the eyes. It is a strong oxidizing agent and gets reduced easily even by the dust or grease to OSO2. OSO4 is used as a catalyst in organic chemistry, particularly for the addition of OH groups at carbon double bond on treatment with hydrogen peroxide. It is a good catalyst for several other reactions also, but it gets poisoned easily and is therefore not very popular. Osmium forms usual oxidation states like ruthenium. Osmium also forms a number of complexes with pi acid ligands such as CO, in which osmium is present in -2 or 0 oxidation state. Iridium occurs in nature as an alloy of osmium and ruthenium. In order to recover it from the alloy, osmium and ruthenium are first eliminated in the manner described under the respective metals. Iridium is recovered by appropriate treatment as the slightly soluble ammonium hexachloride iridate. This substance is decomposed on heating to get iridium. Properties: it is a silvery white metal which is brittle but fairly hard. It is used as an additive to platinum for hardening. It is extremely resistant to attack of acids. In bulk state, it does not dissolve even in aquaresia. It dissolves in a mixture of concentrated hydrochloric acid and sodium chlorate in a sealed tube at about 150 degrees Celsius. It combines with chlorine at red heat to give the trichloride IRCl3 and with fluorine at 600 degrees Celsius to give the hexafluoride. It combines with oxygen when heated above 1000 degrees Celsius to give IRO2. Compounds of iridium. The highest oxidation state of iridium is plus 6. The compound IRF6 is known but is quite unstable. Iridium pentafluoride IRF5 has a structure similar to that of RHF5 and MOF5 and is better represented as IRF4. The oxidation state of IR in IRF5 is evidently plus 5. The plus 4 oxidation state of IR is quite stable. The tetrahalides of IR are known. When IR is heated in a current of oxygen, it gets converted to IRO2. A number of complexes of IR are also known. Some of these are following. The last complex is optically active. All the halides of IR third are so insoluble in water. These are all polymeric, containing IR halogen IR bonds in their structure. The hydrated halides of IR third are monomeric and soluble in water. When alkali is added to an aqueous solution of IR3 positive, hydrated IR2O3 gets precipitated. Iridium basic acetate has structure similar to that of basic acetate of RH and Cr, which has been described earlier. The plus 2 oxidation state of IR is not very common, although IrCl2 having a polymeric structure with the IrCl-IR bridges is known. Some phosphine complexes of this state are known. Vasaka's compound is a yellow in color, has the compatibility of coordinating. The yellow-colored Vasaka's compounds turn orange when it takes up oxygen. When flushed with nitrogen, it releases oxygen and again turns yellow. Platinum. Platinum is one of the most important and useful elements of the third transition series. Occurrence. It occurs only to extent of 5 into 10 raised to the power minus 7% in the earth crust, but in view of its concentrated deposit, its extraction is relatively easier. It occurs mostly in the native state mixed with other metals of the platinum family, Pd and Rh, as well as with copper, iron and gold. Thus, the ore obtained from Urals, Russia, contains about 76% platinum, 11.7% Fe, 4.3% Ir, 4.1% Cu, 1.4% Pd, 0.5% OS, 0.3% Pb, mixed with sand. The platinum metal deposits also occur in California, USA, Brazil, Canada, Borneo, and Australia. Extraction. The heavier metal particles are first separated from alluvial and graved by washing gold. If present, is removed by the amalgamation process. The rest of the ore is digested with aquaresia, which dissolves all the platinum metals, forming chlorides except osmium, which is separated thereby. The solution contains chlorides of the metals of the platinum family, is evaporated to dryness, and the residue heated to 1.175 degrees Celsius. Palladium and rhodium tetrachlorides are thus converted into the lower chlorides PdCl2 and RHCl2, which are insoluble, while platinum tetrachloride and iridium tetrachloride remain as such. On adding water, platinum tetrachloride together with iridium tetrachloride passes into solution, while the lower chlorides of palladium and rhodium remain as the residue. The solution is acidified and ammonium chloride is added when the sparingly soluble salt NH4 to PtCl6 gets precipitated. The iridium tetrachloride remains in solution. The precipitate of ammonia chloroplatinate is ignited when it decomposes to give spongy platinum. It is heated to redness and hammered to get the metal in the form of coherent seeds. Properties. Platinum is a white metal with a silvery luster. Melting at a high temperature of 1769 degrees Celsius, it has a very high density of 21.4 gram cc. It is malleable and ductile. It can be rolled into foils and drawn into very thin wires. It has about the same coefficient of expansion as glass, and therefore platinum wires and foils can be sealed into glass without cracking. It is more reactive than osmium and iridium. It is, however, considerably more resistant to acids than palladium. Pure platinum is not attacked even by hot and concentrated hydrochloric, nitric and sulfuric acids. If the metal is impure, it is slightly attacked by sulfuric acid. However, it is attacked by hot aquaresia, forming chloroplatinic acid. It also dissolves slowly in HCl, particularly in presence of air. Platinum is commonly considered to be an inert element. This is, however, not quite correct. It is attacked by fused alkalis, nitrates and peroxides. Therefore, platinum should not be employed for heating such substance. It is also attacked by carbon disulfide vapors when a compound of composition PtCS2 is formed. It is also attacked by chlorine at red heat. With fluorine it gives PtF4 and with chlorine it gives PtCl2. It combines with oxygen at high temperature and pressure to give the oxide PtO. Platinum, especially when it exists in finely divided states, absorbs an appreciable quantity of hydrogen, and when it fused state it absorbs oxygen. The volume of hydrogen absorbed may be as high as 900 times of its own volume at 80 degrees Celsius under a pressure of 1 atmosphere. Platinum is used therefore as a catalyst like palladium in a number of hydrogenation processes. The mechanism of absorption of hydrogen by platinum is same as that of by palladium. Platinum forms alloy with a number of metals. It exercises oxidation state of +2 and +4 in its compounds. A number of complexes containing platinum in both these states are also known. The +3, +5 and +6 oxidation state are also known. Examples are PtCl5, PtF5 and PtO. The +5 and +6 oxidation states, however, are the +4 oxidation state is more important. Platinum differs from the other elements of its family in forming alkali derivatives by Grignard reaction. Uses: first, since platinum is not attacked by air, oxygen or water, it is used in jewelry, and an account of its bright luster. It is used for ornamental purposes. It is also used in dentistry. As it is not attacked by strong acids even at high temperature, it is used in chemical apparatus such as dishes, etc. For the same reason, it is used as electrodes in various electrolytic processes. Fourth, it is used as an important catalyst in the form of platinized acetose, which is prepared by soaking acetose in a solution of platinic chloride containing a little of hydrochloric acid and ammonium chloride. Some important reactions catalyzed by platinum include combination of sulfur dioxide and oxygen to form sulfur trioxide in the contact process for the manufacture of sulfuric acid. Oxidation of ammonia to nitric acid. Nitric oxide is in Ostwald process for the manufacture of nitric acid. Oxidation of methyl alcohol to formaldehyde. Compounds of platinum. Compounds of platinum 0. A well-known compound in which Pt occurs in the zero oxidation state is this. Platinum, like palladium, does not form a pure binary metal carbonyl. The reason for this has been discussed in the chapter on pi acceptor ligands. Compounds of platinum 1. Platinum monochloride. As already stated, platinum shows variable valency. Univalent platinum is represented by platinum monochloride (PtCl). It is obtained by heating platinum 2 chloride with platinum at 581 to 583 degrees Celsius. However, it is not known in pure state. Compounds and complexes of platinum second. Platinum second chloride. Platinum second chloride (PtCl2). The typical bivalent platinum is represented by platinum second chloride. This is obtained by heating platinum 4th chloride at 580 degrees Celsius. PtCl4 gives to PtCl2 plus Cl2. It is green-gray powder insoluble in water. It dissolves in hydrochloric acid and metal chloride solution forming complex ion. PtCl4 2 negative. PtCl2 plus 2Cl negative gives to PtCl4 2 negative. Thus, with hydrochloric acid and potassium chloride, the following complex compounds are formed. Complex platinum second chlorides are also obtained by the reduction of complex platinum 4th chlorides by sulfur oxide, etc. Potassium tetraplatinate second may also be obtained by warming a paste of potassium. It forms stable salts. The lithium and sodium salts are soluble, while the potassium and ammonium salts form yellow precipitates. These salts decompose on heating, leaving a residue of platinum. K2PtCl6 gives Pt plus 2KCl plus 2Cl. Organometallic compounds of platinum. These have been discussed in chapter 34 on organometallic compounds. Gold occurrence. Gold occurs in native state, either scattered in sand and gravel or mixed intimately in quartz. It also occurs to a small extent in combined state. The mineral sylvanite contains a telluride of silver and gold. Metallurgy. Different methods are adopted for the extraction of gold according to the nature of its source. Extraction of placer gold. When gold is mixed with sand, silt or gravel, its separation is affected by taking advantage of its much higher specific gravity. The OA sand mixture is thoroughly washed with a powerful current of water in long slices. A sluice is an inclined channel with a number of small troughs provided with cleats along the bottom. The heavier particles of gold settle down and collect in the throes, while the lighter particles of silt, sand, and gravel are carried away by the current of water. This process is known as placer mining. And sometimes it is necessary to throw a powerful steam of water on deposits to wash away the gravel, etc. The process is then known as hydraulic mining. Extraction of vein gold. It is popularly known as vein mining and is employed for the extraction of gold from hard auriferous quartz rocks. The rock is blasted at the quarry and the bigger lumps are broken to a smaller size by means of rock crushers. It is then carried to the factory and subjected to the following treatment for the extraction of gold from it. Number 1. Pulverization. The smaller pieces of auriferous quartz are finally pulverized by means of a laterally battery stamp mill. Each of these mills consists of a mortar box enclosing a die and a moving stamp. The stamps weigh over 1,000 pounds each and they fall about 100 times per minute through a height of about 20 centimeters. The auriferous quartz pieces are fed from one side into the mill and pounded by the stamp. The pulverized matter is carried off by a current of water through a screen provided at the other end of the mill. The coarser particles, if any, are retained and pulverized again. Amalgamation. The water slurries carrying the finer particles is next passed over amalgamated copper plates placed in a sloping position in front of each stamp mill. Free gold present in the slurry is retained by the mercury and the tailings dropped into a dump. The gold amalgam is scraped from the copper plates after every 2 hours and collected into a pit below called the mercury well. The used up copper plates are replaced by the new amalgamated plates. Nearly 75 to 80% of the total gold originally presented in the quartz is thus recovered. The rest passes into the tailings. Third, distillation. The gold amalgam so collected is squeezed between rubber blocks and then distilled in iron retorts. Mercury distills over and is collected for further use. White gold is left in the retort. Gold particles recovered from the retort and fused with a flux like borax and made into a solid lump or bar on cooling. Recovery of gold from the tailings. The tailings contain 20 to 25% of the gold originally presented into the quartz rock. For its recovery, the tailings are again passed over amalgamated plates. This results in the recovery of 15 to 20% more gold, while about 10 to 12% of it escapes into the earthy slime or gangue. The treatment of gangue. The remaining 10 to 15% of gold is extracted from the gangue with the help of the MacArthur forest cyanide process. Extraction of mineral gold. The minerals in which gold is present in a combined state are first of all subjected to roasting in order to remove easily oxidizable impurities like sulfur, tellurium, arsenic, antimony, etc. The roasted ore is then to the MacArthur forest cyanide process or the platinum colonized process described below. A MacArthur forest cyanide process. This process is based on the fact that in the presence of atmospheric oxygen, gold dissolves in a solution of potassium cyanide with the formation of the cyanide complex 4Au plus 8KCN plus 2H2O plus O2 air gives to 4KAuCN2 plus 4KOH. The finally powered roasted ore is filled in large vats made of cement or iron and consisting of false wooden bottoms with holes. A solution of potassium cyanide 0.5% percolates all through for 12 to 24 hours. From the complex cyanide solution, the metal gold is precipitated by zinc shavings. 2KAuCN2 plus Zn gives to K2ZnCN4 plus 2Au. For this purpose, the soil is run through wooden troughs containing zinc shavings. Platinum's chlorine process. The roasted ore is placed in vats with false bottom, moistened and then saturated with a current of chlorine from underneath and left as such for a day. The gold chloride AuCl3 thus formed is leached with water. The solution is transferred to a separated tank where it is treated with ferrous sulfate to precipitate gold. AuCl3 plus 3FeSO4 gives to Au plus FeCl3 Fe2SO4 3. Refining of gold. Gold obtained by any of the above process is impure and is generally contaminated with other metals like silver, copper, lead and some other baser metals. Lead and the other baser metals are removed by cupellation, while silver and possibly a small amount of copper remains. The removal of silver and copper from gold is known as parting and can be achieved by the following methods. Number 1. Chlorine parting. The impure gold is melted in a fire clay. The impure gold is melted in a fire clay crucible and dry chlorine is bubbled through the melt by means of clay pipes. At first, fumes of baser metal chlorides are evolved, then silver is converted to silver chloride and the gold remains unaffected. Silver chloride forms a scum on the surface of the molten metal and can be easily skimmed off. The pure gold is tapped out of the crucible into small ingots, parting with sulfuric acid. It is based on the fact that while silver and copper dissolve in hot concentrated sulfuric acid, gold remains unaffected. It is found that if the percentage of gold in the impure sample is more than 25 degrees Celsius, the sample is not attacked by the acid. More silver is therefore added to the sample till to alloy containing less than 25% of gold is obtained. The alloy now becomes attackable by the acid. This is treated with boiling concentrated sulfuric acid when silver and copper dissolves, leaving gold behind. 2Ag plus 2H2SO4 Ag2SO4 plus 2H2O plus SO2. In this process, since the gold content in the sample has to be reduced to 25% or 1/4 before the acid treatment, it's sometimes called quartration. Physical properties. Gold is a third. Electrorefining. Blocks of impure gold made the anode in an electrolytic cell containing solution of gold chloride AuCl3 in hydrochloric acid. Thin plates of pure gold constitute the cathode. On electrolysis, pure gold is deposited on the cathode. Silver forms silver chloride, which remains as a deposit near the anode. Gold thus obtained is 99.9% pure. For a higher purity it desired, the metal is put to second electrolyte refining. Physical properties. Gold is a yellow metal, highly malleable and ductile. It has a specific gravity of 19.3. It is soft and therefore used in coinage and jewelry. It is necessary to alloy its silver or copper. It is very good conductor of heat and electricity. Mercury. Occurrence. Small quantities of mercury occur in free state, disseminated in rocks. In ore, cinnabar, HGS is found chiefly in Spain and Italy. Extraction. Cinnabar. HGS is crushed dry and screened into two grades. The large size pieces richer in the ore and sorted and subjected to combined process of roasting and distillation. HGS plus O2 gives Hg plus SO2. Various types of furnaces have been used for this purpose, but the most important is the Iridian furnace, which is refers to chapter 10, purification. Mercury obtained as above contains iron and zinc as the main impurities. Some dust particles and mercury oxide are also present in the form of scum, which however can be removed by squeezing mercury through chemist's leather. It may be further purified by vacuum distillation. Physical properties. It is a silvery white metal and liquid at ordinary temperature. It may be recalled the metal atoms in a transition metal are bonded together through both the covalent bonding and metallic bonding. The covalent bonding, which is much stronger than the metallic bonding, is mainly responsible for the hardness of the metal. It involves the overlapping of d orbitals of the metal atoms containing unpaired electrons. The weaker metallic bonding is due to the attraction between metal cations and negatively charged free electrons surrounding. Therefore, the attraction between mercury atom is quite low. Consequently, mercury is soft compared to other transition metals. Further, the ionization energy required to remove the valence s electrons of mercury